All right. Oh, I gotta turn that on. Cool. All right. Hello, everyone. Welcome to this week of CSE 365 Intro to Cybersecurity. We are on to a new module, as hopefully you're all aware. Building web server completed on Monday at 0 o'clock. And reverse engineering is the new module. I guess let's make sure that the Twitch stream is working so that the people at home are also able to listen. Twitch people, can you hear me? Let's see here. I guess we can also make sure. Okay, OBS is switching my screen. I can see my camera. Wait, can I see my mic? Yes. Mike says audio is happening. And people say it's good. All right. We'll take their word for it. Yeah, so welcome to 365. We're on a new exciting module. I hope that you all have been having a lot of fun with assembly because guess what? As one of the memes says, it's assembly again. Reverse engineering. So hopefully this will be the last assembly module for a while if you're really sick of assembly. But all three of these assembly-ish modules are coming at it from a different perspective. So assembly crash course, of course, is just like the basics of assembly. Like let's write some basic snippets of assembly. Building a web server, let's write a real program. And now reverse engineering is, instead of writing assembly, you're lucky. You don't have to write any assembly in this module. You're going to read assembly instead. You know, you gotta learn how to write a language and how to read a language. Well, this is the reading part in reverse engineering, as well as we launched also in this module with the 8 levels of, I guess you can see here, it's called MBO a very quick basic walkthrough of GDB. So don't panic that maybe you're like looking at this and you're seeing like 2 modules have been released together or something. The GDB portion should hopefully not take you too long, though I do encourage you to really pay attention to it because GDB is a very useful skill. And then also Baby Rev. So I guess for those curious, Baby Rev has come down from CSE 466. So I guess for those unfamiliar at this point, this class follows a model that's very similar to CSE 466. Both run on the dojo. Initially, the dojo was created for 466. Then we applied 365 to it. Well, reverse engineering is one of the modules that has been present in 466 from basically the start. You can see here that there's a reverse engineering module. And guess what? It's the same levels. It's the same challenges. It's no longer going to be in 466. Now it's in 365. But don't panic yet because you're thinking, oh, this is like a 400 level class. Why are we doing 400 level stuff in a 300 level class? There's kind of a split in the 466 material here. You can see that in our case, we go up to 11.1 for Baby Rev, and 466's version just keeps going with several more levels. Turns out that 11.1 versus 12.0, it's more difficult, let's say. And maybe that's not actually reflected in the solve count, but that's probably due to external reasons, not anything actual. Once you get to 12, it goes on to a whole different world of reverse engineering. And so we're bringing the first half of that module into 365 for those curious. Okay. So it looks like we got a lot of speedy people. Some portion of people have completed, maybe one person, I guess, has completed everything. And then our first ASU student is 2 solves away. It's very exciting. Okay, so that is the reverse engineering module. I encourage you to watch these videos, get an understanding of reverse engineering. I guess, again, so in case you're curious why the lecture videos here aren't me, you're going to see that's definitely not me. That is Jan Shoshitashvili, who teaches CSE 466, and that is why the lecture videos are of him. Don't worry, I helped him create 466. I very intimately familiar with all of these challenges, happy to answer questions and discuss everything as we need to. Before we do that, let's take a quick look at the memes from the last week. So I think we basically saw all the memes up until like Valentine's Day or something. I think there's some good Valentine's Day memes. Though I will say that the quality of memes has been dropping and it's very sad. Let's see here. Is there anything? I know these are all the liked memes, but even the liked memes are like questionable. This meme is terrible. It has literally nothing to do with the class, but I guess it is a funny meme. Let's see here. Let's see if there's anything actually relevant here. Oh yeah, this is a good one. So hopefully you're familiar with uh, how Discord works. But when someone helps you, you can right click on their message and hit app thanks. So that's how you thank people. In case anyone's still unfamiliar with that, if someone helps you, thank them. I mean, I guess you don't have to, but I don't think they're going to help you again if you don't thank them. They're going to be very sad. A lot of people were dealing with TCP stuff. Don't worry. Guess what? After this module, I think the next module, pretty sure we have to confirm that, is a networking module. So TCP, how does it work? Connection reset by peer. Well, that's going to be the next module. You're going to understand what this connection reset by peer really means in the next module. Python 2 stuff. What is this? Oh, yeah, this is hopefully at some point in your lives you will learn how to not wait for the last minute. As basically, it's a good lesson. Almost certainly, if you're waiting to the last minute at this point in your life for everything, you'll probably continue to do that for the rest of your life. But good luck. Level 11. Yeah, so now we're into reverse engineering. We got GDB, we got IDA. We got a whole bunch of tools to talk about in this module. That'll be very cool. Yeah, so embryo GDB is definitely going to be a lot easier than baby rev. Don't know what that meme means. Okay, this one. So if you've done any sort of debugging that's like dynamic in nature, I guess, would print debugging be dynamic? It's like, I guess that would kind of be dynamic. But if you've ever used a debugger, trust me, GDB is not that scary. If you've used Visual Studio Debugger for like debugging C, I've never actually used Visual Studio Debugger. I'm sure it's great. But GDB is also great. So we're gonna look at GDB. It's gonna be awesome. Under the hood, almost certainly Visual Studio Debugger. Well, they probably actually implement their own. They're probably not actually using GDB, but they're using the same. It's the same concepts. You'll see. It's not so bad. Wait, did it just loop? Why did it loop? I think it looped. Okay, cool. Anyways, that is our memes. Let's jump into the new module at last. Let's see here. Okay, does anyone have any super high level questions before we jump into the module? Okay, then before I take like specific questions, like I'm seeing someone ask about 5. I'm guessing it's GDB 5 and maybe GDB 3. Let's take a look at GDB 1 so that we can make sure we all understand the style of the challenges here in this module. In fact, we're going to look at embryo GDB level 1, and then we're also going to look at baby rev level 1 so that we can make sure, I mean, they're both different styles. So we want to make sure we understand the style of both of these challenges. So we start up embryo GDB level 1. And we're in practice mode. We'll come over here, SSH in. Of course, you can do this through any way of accessing the challenge. Okay, so as always, we look at the challenge directory, right? Hopefully we're all familiar with this. I do challenge and I hit tab to just tab complete it. Challenge, and I just hit tab. That way I don't have to like guess what it is. Otherwise you could ls the directory. But we are launching challenge embryo GDB level 1. We hit enter, and this is what we see. So it says the program is restarting under the control of GDB. You can run the program with the GDB command run. So this is the GDB startup message. In fact, if I close this and I do GDB bin cat, and I hit enter, guess what? It's the same startup text. It's literally just launching GDB as part of the challenge. So it restarts the challenge under GDB. And now basically the challenge like attaches GDB to itself. It's kind of insane that it's doing that, but that is the style of this challenge. So we're just immediately in GDB. So we can see that it's accessing the challenge embryo GDB level 1 thing. It says it doesn't find debugging symbols. That's fine. We don't really care. what we can do now is we can type, as it tells us, run. And run, what run does is, guess what? It's very simple. It runs the program. So we type run, and we get a whole bunch of text. So it says starting program, challenge embryo GDB level 1. This is GDB telling us this. And now we get a bunch of output from the program itself. So there's kind of two different types of input that are being intermingled here. We have GDB output, we have program output. It doesn't really matter who's saying what, but that is what's happening here. So it tells us, welcome to the challenge. It tells us, hey, GDB is cool. You're running GDB. The program is currently paused. I encourage you to read this text because, believe me, GDB is, the meme is not wrong here. This meme, I guess we lost the meme. The meme saying that GDB is like terrifying or whatever, it's not totally wrong. GDB is like a language in and of itself. But learning how to use it can be very useful depending on what you're trying to do because it allows you to just fully introspect a program and just basically walk through it instruction by instruction if that's what you want to do and look at all the registers, look at memory, just fully understand the state of a program at any point in time. And this quick 8 levels of walkthrough are going to teach you a bunch of the basics of doing that. So we can see right here, there's a whole bunch of ways to run the program, start the program, do something like that, like get things rolling. So we already started with the run command, and the run command just launched the program. Well, there's also the start command, and the start command just starts the program, right? So if we do, let's see here, GDB, so let's clear cd temp. So if we run bin ls, right, we know what's going to come out of that. If we do gdb bin ls, and we type run, guess what? We can see our output right here. We got our bin ls output. In fact, I'm going to zoom in a little bit more. However, if instead we start up GDB and we type start, well, guess what? Well, first thing it does is it says, hey, do we want to maybe do a breakpoint? We're just going to say no. And in this case, also, it just prints out the output. Now, the reason for that is because we said no to this, and this program doesn't have a symbol saying, hey, where is main? So by default, GDB tries to, and we're going to see what this concept means, but GDB tries to set a breakpoint on main, which means it's just going to pause the program from continuing at main. And since there's nothing called main in bin ls, it just runs through everything because there's no breakpoint. Instead, though, and as we saw above, there's also start I. So if we do this and we type start I, well, now it starts the program and it breaks it just immediately at the entry point of the program. So you might be thinking to yourself, I thought main was the entry point to the program. Like the program starts at main. What do you mean there's like something before main? Well, it turns out there is stuff before main and it pauses there. Main is like a C runtime thing that eventually main gets called. But there is code that technically executes before main. And when we do start I instead of start, it pauses us at that very initial point. So this is just kind of 3 different ways, right? We got run, we got start I. 3 different ways to start up our program. Now let's go back to the challenge. Actually, we will relaunch the challenge just to make sure we understand what's going on. And we type run, and it tells us, right, start, sets a breakpoint on main. We got start I, breaks on underscore start, and we got run. So it's just no breakpoint. So, and then there's also other things you can do. You can attach to an already running process. You can look at a core dump, which basically means, hey, a program crashed. Or, I mean, there's multiple reasons to have a core dump. But if a program crashes, for example, and it produces a core dump, it's just a snapshot of the program at that point where it crashed. And you can use GDB to analyze that core dump as well. Okay. And then it tells us, okay, there's also other ways you might start your program, right? You might want to start the program up with a bunch of arguments. And you might want to redirect standard in. There's kind of like flavorful ways to start up your program. And then if we want to continue execution, so we can see here we're currently paused. And you might be thinking, why are we paused even though we typed run? That's like maybe confusing. The reason for that is these challenges like self-insert their own breakpoints. And that is what's happening. So you can see here, program received signal sig trap. Trace breakpoint trap. What that means is it hit an int3 instruction. So an int3 instruction, as I think we talked about in the embryo or in the assembly crash course module, int3 is basically like stop the program, pause the program, like do some sort of debugging stop of the program. And GDB actually under the hood does the same thing. When you'll see eventually you set up breakpoints. Under the hood, when you set a breakpoint, it is inserting an int3 instruction at that location, and that's how it does it. Okay, so it tells us type continue to continue execution. So we type continue, and guess what? Level 1 is super straightforward. You win, here is the flag, and it just spits out the flag. So all you needed to learn how to do was type run and type continue. Very simple, basic commands within GDB, but that's kind of the beginning point of GDB. Okay. Also, anyone asking questions in the Twitch chat, you just say a level. I mean, maybe we'll get to it, but if you ask a question about the level, it's probably 10 times more likely we'll get to your question. Anyways, that is Embryo GDB level 1. So that is the style you're going to see. You're just going to be using GDB in different ways, and the challenge will be kind of walking you through how you should be using GDB. Okay, and then just to show the other style of challenge, let's look at Baby Rev level 1. So if we hit practice on this, let's see what's going on here. Yeah, there's a question. Yeah, I did say that. Is practice mode useful in this module? I don't think so. I don't think you need practice mode in this module. I have to think about that again. I'll definitely say if we notice that you need practice mode for some reason. I don't think this module should need practice mode though. Okay. So we run challenge Baby Rev level 1, and this is the other style of challenge. And we run this, you're gonna see we don't see a bunch of GDB output. We just have a program. It's some program. It was, just in case you're curious, it was written in C and compiled, and all you have is the binary, right? So if we look at this, Baby Rev level 1, if you've been catting out the challenges before to this point, I believe all of them up to this point, if you've just been like catting them out, you would have seen that it's just like a Python script. Well, when you cat this, you're not going to be very happy. It's a binary. It's like you can see all these crazy symbols. This is not meant to be catted. You technically can cat this file, but it's not really human readable. This isn't how you reverse engineer. You don't just cat a binary. I mean, you could probably get something out of this. We can see like a bunch of the text that's in here that's at some point going to get output, but it's not probably going to be your favorite debugging tool. So this is just a binary. It's compiled from C, and you're going to be analyzing it. So we can see that what this program does is it prepares to give you the flag. However, in order to give you the flag, it consumes a license key over standard input. So this is modeling a licensing system, right? Where you have some program, and the program requires a license in order to be able to correctly run it. This is modeling that concept of a license generation, and it turns out you could use reverse engineering. I mean, it depends on the context of a program, and we're not going to look at real world programs for this. But if you reverse engineer it, you can reverse engineer the program to figure out what the license key is, and in doing so, get the flag. So basically, the moral of the story is you're going to be reading or reverse engineering these programs, and we'll see what that looks like here in a second. So it says ready to receive your license key, and it's just paused. And it told us before that it's receiving it over standard input. That means if I just send it something, hopefully we're going to see that it no longer is paused if I type it like hello and hit enter. And sure enough, that happens. So this style of challenge, we have these 1.0 versions and these 1.1 versions. Now, what's happening there is that you have to solve them both, first of all. But the 1.0 or the .0 version of the challenge is going to be what's called a teaching challenge, which means the amount of output is, there's way more output going on. So you can see all of this. It says initial input, the mangling is done, the final result of mangling input, expected result, blah, 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 blah. All of this happens in a .0 version of the challenge. In a .1 version of the challenge, you're not going to get all of this output. So we'll just to make sure everyone's understanding what's going on, we'll look at the .1 version also. So we send it hello, and it says initial input. This 68, 65, 6C, 6C, 6F, in case we're curious about that, right? If we take all of these characters, right? This is car int I16 for I in that. Whoops, that's not correct. Right, this is just the hex output of what our string is. So 68, 65, 6C, right? Car 0x68 is H, etc. Right? So it's just telling us what we gave it, but it's telling it to us now in hex. And the reason for that is it's going to start mangling stuff. So we can see the mangling is done. The resulting bytes will be used for the final comparison. Final result of mangling the input. Well, it doesn't look like it did anything, and that's because this is level 1. The mangling is basically a no-op. It doesn't actually mangle it on level 1. So 68, 65, 6C, 6C, 6F. So 68, 65, 6C, 6C, 6F. And then it says, well, I didn't expect that. So, well, eventually it says, checking the received license key, wrong, no flag for you. It says, I expected this right here. So clearly this right here versus this right here, these are different. And so we can very clearly tell that we provided the wrong license key. We'll see that the .1 version, again, is not so helpful. But let's see what we were supposed to give it. So if we look at this and we convert that to ASCII, right, we've got this string right here, pxffg. So if we rerun the challenge baby rev this, and we send it pxffg, we can see initial input, result after mangling, expected results, checking the received license key. You win. Here is your flag, pwn.college practice. Now, this might just sound very simple. Like, why are we doing this thing where we're just like copying and pasting whatever expected result is? This sounds nothing like a key gen or a program that takes a license key, right? Why would a license key validator tell you the license key? Well, the reason is that we're in the .0 version of the challenge. In the .1 version, it will not tell you. And what you're going to have to do instead is you're going to have to, effectively what you're going to have to do is cat out this program. But you're not going to use cat. Cat is not the best way to look at this. You're going to use something like objdump. And I'll show you a number of tools that we can use for looking at this. We'll start with the simplest one, which is objdump. So if we do objdump, so there's a whole bunch of flags going on here. This dash capital D means disassemble the program. This means give it to me in Intel syntax. And then this is the program that we want to dump out the contents of. And we're piping it to less so that we can scroll through it easily. So we can see that there's a whole bunch of assembly, right? This is allowing us to see the assembly of our compiled C program. So I'm going to jump to main, and I just typed slash, and then I typed in main, and now I'm hitting enter, and that is jumping me to main. In fact, actually, let's just do this in a simpler way, maybe. And we'll send that out to temp out, and then open up temp out in our favorite editor or whatever, right? And now I'm jumping in my favorite editor to main, right? And right here, we can see this is where main is. So when you write a program, right? Test.c, right? We're writing some C program, and we say puts hello world, and we have our main function, and our main function is what the beginning of our program is. Well, guess what? That is right here. This is main. And this is all of the code responsible for whatever is inside of main. So if we look through here, we can see a whole bunch of stuff is going on. And it's going to be, you're going to learn a lot of skills in going through all of these programs. Namely, what kinds of instructions to pay attention to, which ones you can ignore. It's kind of a skill, a kind of foundational skill of reverse engineering, is that probably you're not just going to go to main and just start reading every single instruction and saying, what does this instruction do? What does this instruction do? What does this instruction do? At some point, you're going to want to learn what all of this stuff is doing because it is important. So this right here is all very standard stuff. you're going to see a lot of programs that do this sort of stuff. There's a lot of patterns here, but we're going to ignore that for the moment. So, for example, what we could do if we wanted to just very quickly ignore a lot of stuff is we could just look for all of the call instructions, right? If we look at call instructions, then we know what sorts of functions main is calling. So I'm just searching for call, and we can see call, it calls assert fail. We'll ignore that for a second. Let's just look at all of the calls. So it calls assert fail, it calls puts, calls printf, puts, put character, set vbuff, puts, read, puts, put character, printf, puts, printf, puts, put character, printf, right? We've got all of these functions. Eventually we can see another one, mem compare, and then we have call win, and then we call exit, then we call puts, then we call exit. Obviously, this isn't the order necessarily that all of these functions are being called. We have this concept of control flow within our program. It's not just going to go through function by function and call all of these functions in order. We might have jump instructions somewhere in here. We might have compare instructions somewhere in here. We might have test instructions, which is similar to a compare instruction. So for example, right here, we can see that there's a jump. That means there's some sort of control flow in here. And when we're using objdump, we're just really linearly looking at this. And it's not necessarily the easiest thing in the world to look at, right? We're just looking at a linear blob of assembly, and we're wondering what the control flow of this program is, right? Control flow is an incredibly important attribute of a program, or let's just even say of a function. A function's control flow really tells you a lot about the function, right? The function doesn't just execute linearly in order. Similarly, what kinds of functions it calls is super important. Again, you might not call those linearly in order, but this kind of combination of what will my function call and what does it need, what does the state of the program need to be in order for the control flow to go in that direction where it will call that. These are two important things, right? If we think about it, if I have, what do we want to say? Car or int, argv, car, well, that's not right, argc, and I say if argv1, if argc greater than 5, right, we pass more than 5 arguments. Oops, we are typing terribly right now. And I say it was more than 5, else puts it was not. Right, this is a very simple program, and maybe we'll also say win, void, win. Maybe we'll put the win here. And this void win, we're not going to define what win does, but who cares, right? We've got this program. There's kind of two important aspects of main. We have the control flow and we have the functions it calls. So maybe we look at main and we start saying to ourselves, well, guess what? This win function, and I'm going to tell you right now, the win function is pretty good. The win function is how you win the challenge. It's what's going to ultimately give you the flag. And we can look at that in a second. If we look at this win function, we can see that main is capable, potentially, at least there's a call instruction for win somewhere in main. Now the question is, how do we reach that? I just told you all these functions aren't just going to be called linearly, and we know that, right? We've written a C program, right? If we look at this sort of program right here with main, only in the case where argc is greater than 5 will win be called. Now, if we assemble this, in fact, I'm going to go through and assemble this. Oops. Show gcc test.co test. Oh, we need win to actually do something, or we'll just give it an empty definition. Warning, implicit declaration of puts. That's fine. That's fine. It's just a warning. Okay. Now we have this test program, right? So we run test and it says it was not. But if we say A, B, C, D, E, F, right, it was more than 5, right? It's a very, very simple program that has some basic control flow. And if we go down the same path of disassembling this, temp test, and we're going to redirect that to test disassemble or something. And we look now at test disassemble, right? It looks very similar. We go to main eventually, right? We're looking at a very similar program that we were before. It's just this time now we do a number of things. We call puts, and we call win, right? So this is our call instructions here. And now we have a better understanding of what this program actually does in our head because we just wrote the C and read the C. So already in your head, you know what this program does because you've written C before. Now we'll do this. You've written C before, and you are probably, at least maybe you don't like C that much, but you're at least somewhat confident in your ability to read something that looks like this, right? You know what an if statement is. You know what a function call is. You've read stuff like this before. You've written stuff like this before. This, you can like emulate the behavior of this program in your head. Well, what reverse engineering is going to require you to do in the context, at least of this module, where we don't have the original source code, is to be able to build up those same skills of reading this and understanding, like, how do I possibly hit this win function? Except you don't have the source code anymore. So this is the goal of this module. And we can see that we have our call puts, our call win, our call puts. And as I was saying before, right, these three things aren't just called linearly in order, as you can tell here, right? We've got a condition in here. And right here, right, we can see that condition. Right here, we can see a compare of something with 5 and jump less than or equal to main plus 0x31 or 1185. So 1185 is right here. And then it's going to call puts and then blah, blah, blah. Otherwise, it's going to fall through. It's going to call puts. It's going to call win, right? This is the basics of this program. Now, so as I said, what functions it calls, what the control flow is, those are two very important concepts. And this is how we're looking at it right now. Now, there are better tools here for allowing us to look at a program. So right now, we've just been using objdump. And it's just a blob of instructions. Technically, the control flow is embedded in there because we have stuff like jumps in there. But maybe we want to very directly see that control flow. If we want to very directly see that control flow, this is where we're going to use a tool like either IDA, Ghidra, or Anger Management. In this case, we're just going to open IDA. Okay, so we can see, actually, let me make sure we are very clear, right? We click on IDA freeware, we click this button, we click OK, and then we're going to say go. Whoops, no, that's not what we're going to do. Click IDA, OK, new, disassemble a file. What we're going to do is we're going to go to slash, we're going to go to temp, and we're going to load up our test program. And then we're going to hit OK. And look at what we have here. We've got our control flow. So now we can see why, well, I mean, maybe we already know why control flow is called control flow, but we can very quickly visualize control flow. This is, and I don't know if there's a way for me to zoom in. Let's see here. Oh, that works. But I guess that's not necessarily helpful. This is the exact same thing as our objdump thing. It's just now it's in a graph form. We have, right, the exact same stuff. We've got our main function here, and it's doing a whole bunch of fancy stuff. IDA definitely does more than objdump. And one of the things it does is builds out this control flow graph. So we can see right here we have our compare RBP plus, and it's doing a whole bunch of stuff, as I said before. Before we had compare dword pointer RBP minus hex 4 with hex 5. We do technically have the same thing right here, RBP plus var underscore 4 5. And then we can see that var 4 just means minus 4, dword pointer minus 4. So minus 4, right? It's technically the same thing, minus 4, and then we can see var 4 is minus 4. So it's the same thing, but it's doing abstractions. And you're going to see that at some point, our goal as a reverse engineer is a number of things. I mean, our goal is to understand what's happening. And we just said that if I gave you the source code of a program, you would probably have a better time understanding it than if I just gave you all of the assembly of that program. And the reason for that is abstraction, right? We want to just start taking a bunch of instructions. And so normally we have some program and it's written in, let's say, a high level language. Of course, C is not a high level language, but it's certainly a higher level language than assembly. And we have all these abstractions built out, and then we compile it and just put it down to the bare metal thing that actually runs, right? We take abstraction and we go down the stack. In the case of reverse engineering, you're going back up the abstraction stack, right? You're kind of going the opposite direction as you normally would. And objdump is the first tool, right? It's better than just a bunch of bytes in a file. At least we get to see the instructions that represents those bytes. IDA gets to bring us kind of one step higher, or actually several steps higher. But one of the ways it does that is this control flow graph, right? We can see here that we can call win, and here we can, puts and then win, whereas here we just call puts. And we can even see these strings in here, right? It was more than 5, it was not. So this is even just immediately telling us what is the underlying data that's about to be putsed. So, right, if we look here with objdump, that all we have here is this. We have load effective address RDI RIP plus 0xe90, and then we call puts. So we're setting up the argument for puts by putting something into RDI. We have no idea what we're just about to output by looking at it like this. So we're like, as far as we know, we're outputting something. We truly have no idea. Well, IDA's kind of being nice, and it's telling us what we're about to output. You can see that it's pulling this string out of here, so that's cool. Let's see here. And then we can see the end, right? So this is the graph, right? The program, or this function in particular, is going to take some path through this graph, right? It's going to go from here, and then it's got to go to one of these blocks. And then we can see that these two blocks merge back in at the end as this program gets ready to exit. You can have really complicated control flow graphs. This is clearly a very simple one, but this could get way more complicated, way faster. But probably this graph representation of the control flow is going to be much easier than just a linear blob of instructions. Now, there's one more thing. So we said that if we could read the source code, we would probably be able to read this a lot quicker. Now, the source code is gone. We lost the source code. As soon as you compile a program, if you delete the source code, the program still runs, but the source code is no longer recoverable. It's not like the source code is somehow embedded in that program other than the artifacts of compiling it. Now, if we, one more thing, I guess. If I hit space, so I'm in IDA and I'm at some instruction and I hit space, we can get back to a linear view in the same way that objdump gives us a linear view. So that's pretty cool. So we can go between graph view and linear view with a space. Now there's one more thing we can do, which is very cool. And you don't want to rely on too much, especially for these challenges, but I'm going to show it to you anyways, even though in some sense this is probably going to make things harder for you in a lot of ways. In a lot of ways, it'll make it easy. This is dangerous. Even though I'm going to show this to you, this is going to be very cool. If I hit tab and then hit yes, it decompiles the program. What that means is it's the reverse of compiling the program. It's going through and it's using all of its program analysis, heuristics, whatever, to take that assembly and do its best effort of creating source code that would then compile back to the original. It's basically undoing the compiler, which maybe to you sounds like a very easy thing, but I can promise you it's very difficult to undo the compiler. This is a very hard thing to do. But IDA and anger management and Ghidra and a lot of these tools, not objdump doesn't have a decompiler, it allows you to, in some sense, recover the source code. Now, the source code it probably won't be incorrect, but at some point, the source code might be more difficult to read than the assembly. And that sounds insane, but I promise you that there will be circumstances, and we'll see as you go through this module, where it is not easier to read the source code. It is actually easier to read the assembly. Trust me, you're going to realize this eventually. But for a lot of use cases, reading the decompilation is easier, right? We can see if argc less than equal to 5, it was not, else it was more than 5, it was not, it was more than 5, or when. Well, so yeah, we can already see, right, that this decompilation is technically not wrong, but it's also hard to say that it's correct, right? In this case right here, we're passing this string to win. Now, it's not wrong in some sense because the value that is in RDI right here, if I jump back to the disassembly, right, we can see that we put something in RDI, and we all know that RDI is the first argument to a function, and then we call puts, and then we put 0 into EAX, and then we call win. Well, technically, something is still in RDI, and so this is why I'm saying, how do we know whether this something in RDI was just an argument for puts, or if it's an argument for puts and for win? And the answer is we don't know. And this is why decompilation, this is like a basic hint at why decompilation is very difficult, is we kind of have to guess. So technically, RDI is set up with that string. So technically, we kind of, in some sense, are passing that to win. If win randomly decided to use RDI here, even though we didn't tell it to, it wouldn't be wrong. But we all know, right, the source code that we wrote, win does not pass that string. We didn't do that. That never happened. That's a lie. And then also, another like trivial case is that we can see that the order of our if and else just kind of got inverted. Right, this is saying if argc less than or equal to 5. Well, I was writing if argc is greater than 5. So it just kind of inverted this condition, moved this block up to the top, and then moved this block down here. It's correct. It's just that's clearly not the source code that I wrote. Now, still, this is probably easier to read than the assembly, but this is tricky. Okay. So this is decompilation. So tab is kind of how you go between decompilation and not decompilation, and space is how you go through graph and linear. And I think you can go from linear also to decompilation. Yeah. So tab to go between disassembly and decompilation, and space to go between graph and linear. Yeah. Cool. Let's see if there's any questions in here. Not seeing anything immediately. Oh, actually, one more thing. Let's. So we wrote this program, so we all know what this program does before we even opened up IDA, so maybe it's not that cool. Let's actually look at the, how do we do this? I don't care. IDA does a whole lot of annoying things, but it does a lot of cool things too, so we use it. So let's open up IDA, and let's look at the actual challenge program now. So we'll disassemble a new file. We will go to the challenge directory. We will click on baby rev level 1. And again, this is all using the desktop view of the infrastructure, so you don't need to install IDA or anger management or Ghidra or anything. If you don't want to, you could also install it locally. It's pretty straightforward to do that. So this, hopefully, this is going to be an annoying thing that almost everyone is going to face if you use IDA when you look at the challenge. If I click new, and I click on challenge and then baby rev level 1, and I double click, it's going to say challenge baby rev level 1.0.i64 permission denied. Please specify another file path for the database. What does that mean? What do you mean permission denied? Why is there permission denied? The issue is that you don't have the ability to create files in this challenge directory, and so you're getting a permission denied. You just hit OK. It's totally fine. And instead, you're just going to specify, basically, IDA, when it's doing its decompilation and analyses and blah, 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 is creating this .i64 file to start storing results. You can't store that in the challenge directory. That's why you're getting permission denied. In this case, I'm just going to save it in the home hacker directory. So I'll just hit save. And now I hit OK, and we're totally fine. It said permission denied. Don't panic. Just hit OK and save the i64 to somewhere else. And now we're looking at the challenge in IDA, and we can see there's more code. It's still not that much code, but we can see here that we've got some sort of assert fail, and this assert fail, like we're just looking at strings and calls in control flow, right? We can see that there's some argc greater than 0 assert fail. So it's basically like asserting that the program has more than 0 arguments. It's just some random thing that the program does. We can see here is where it starts printing out the welcome text. What else happens? We got here telling us it's a license verifier. And then we've got this. So before we weren't actually able to see a loop. We can see that there's a loop in here very easily because look what happens here. We've got this block that goes down to this block, and then it comes back around and comes back to this block. So there's like a cycle in this control flow, and that's because we got a loop. So it's just going to keep going through this loop, and then eventually, clearly, there's a different way out that leaves the loop, right? This way doesn't have any way of coming back here, it seems. So this would come here, then we can come to here, and then here, and then here. Like we can see all this control flow. And it's a little complicated, but believe me, I mean, real programs have much more complicated control flow. There's not too many blocks here. You could conceptually reason about all of these blocks and what they do and how they all interconnect to each other. And this is what you're going to do as you learn how to reverse engineer. This really isn't so bad. So we have a whole bunch of stuff. So really what we're interested in, though, is the win function. So I told you your goal in these challenges is going to be to win. So we can see that this block right here has call win. So how do we get, so really our question is, how do we make the program go here, right? This is ultimately what our goal is as a reverse engineer. We have an objective. So, I mean, in reverse engineering, you might have different objectives. One might just be the simple case of like, I just want to understand the program. In the case of these challenges, your objective is a lot more directed. And your objective is to call win. And so if we just start going backwards to the graph, we can maybe start figuring out kind of in our head executing this program backwards. So we want to call win. How do we call win? Well, at some point, we're going to have to execute this block. And it looks like no matter what, we're going to be executing this block. Well, no, not no matter what, because this could go here or it could go here. So we can see in one case, we get our call win. In the other case, we get wrong, no flag for you. So clearly, this is a really important block. This block right here decides if we call win or if the program tells us wrong, no flag for you. So this block is really important. And it tells us also that it's going to output checking the received license key. And we can see here that this is where it calls memcompare. So memcompare sounds pretty useful, right? We're comparing something. We're going to be comparing RDI and RSI, right? That's how we pass arguments. RDI would be the first one. RSI would be the second one. So we can see that RDI is whatever RAX is. Whatever RAX is whatever RBP plus buff is. So this is, who knows? We have to look at other parts of the program to figure out what this nonsense is. But we also have RSI, and RSI is just expected underscore results. So IDA is just like doing some abstractions. It knows that there's somewhere in global memory, there's something called expected result, and it has a symbol associated with it, and that's why it's able to extract this information. And we can see that it is just a string, right? PXFFG. Well, guess what? That was our string before. So clearly that is useful. So we're comparing PXFFG with whatever is in RBP plus buff. So we have to figure out, continue going, how to make RBP plus buff equal to this PXFFG thing. And this says it does a comparison. To get here, what else do we do? This does something. We're just like, you're just reverse engineering. You're just like looking at this program and trying to make sense of what it all does. So in here, we can see that there's a call to printf. So this is printfing with this %02x thing. So this is how it's printing a bunch of stuff in hex. So this is some sort of loop that maybe we'd want to understand. And then we've got this call, printf. We got expected results. So really what we're looking for is this RBP plus buff. So maybe if we highlight buff, we can see, right, I selected buff, and so now it's highlighted yellow. Well, now I can see everywhere that it's highlighted yellow. So I kind of want to pay attention explicitly there. This is also looking at RBP plus REX plus buff, which means it's some offset into our buffer, and then it's calling printf. So that's not allowing us to necessarily modify this. This is another printf. Let's see here. What else do we have? Okay, well, up here at the very beginning, well, I guess it's not the very beginning, but we also got up in here in this block, we've got a whole bunch of RBP plus buff stuff. And this right here calls read. So we can see right here that we take RBP plus buff, we put that into RAX, and then we put RAX into RSI, and then we call read. So this right here, this is something that we in our head would be looking for. And the reason we're looking for it is this is a way that we can bring input into the program. So this calls read. It brings a bunch of data into RBP plus buff. And so that's how these are all interlinked. Now, we can also take the other approach, right, which is to hit tab. If we hit tab, guess what? Now we've got our decompilation. And again, decompilation might be tricky, but it's useful to at least try the decompilation. If the decompilation looks terrible, like go back and forth between the decompilation and the disassembly. Definitely in the case of these first levels, the decompilation is going to be fine. But you're going to see that at some point, when we start doing like bitwise logic and like flipping bits and like mangling bytes in weird ways, its representation of doing that in C is going to be way more confusing of what that looks like in assembly. So this right here, right, it does a bunch of puts. We can see right here, right, this is that read we were talking about. It does read. Can I zoom in somehow? Let's figure out how to zoom in IDA. We'll ignore it for now, but eventually I'll figure out how to zoom in for us to be able to view this more easily. Actually, it's probably really important. Let's see here. File, window, let's see here, options, fonts. Let's boost the font up to 20. Okay, cool. Someone else says control scroll wheel. Do this for now. This is probably too big, but whatever, we'll roll with it. So somewhere here, right, we've got our call to read. So we call read, and we can see that we're passing it a buffer, right? So we're reading from standard input into some buffer. We're reading 5 bytes, right? You've written assembly that looks like this on how to achieve this, and this is, it's the same thing, right? We're just reading into a buffer. Probably in your web server, you were reading into the stack, and you're just using the stack as some buffer. So we're reading into the buffer, and then we're printing a bunch of stuff. Let's see here. Hold on. Let's use this up arrow. So we read, then we print out a bunch of stuff, and then we do this mem compare, right? Then eventually we just do mem compare, our buffer, expected result, 5. That's correct. We go to win. Otherwise, we print wrong, no flag for you, right? Very simple logic. So we can see that all we need to do is pass this mem compare to pass the win. Looks like buffer doesn't actually get mangled in the case of this level. And so we're able to just look at whatever expected result is. You can see that that's PXFFG. So you'll notice actually what I just did real quick is I double clicked on that thing. So we have this expected result. I double clicked on it. And this just brought us into the data section of the program, which is just a bunch of globally defined data. So that's where somewhere in our binary is PXFFG, literally just those bytes sitting somewhere in some section that's going to be in global memory. So that was there. IDA allows us to do a whole bunch of stuff. So for example, I could right click on this and I can hit this thing called xref graphs 2. Maybe not. Well, I can definitely just hit X. So if I select this and I hit X, this shows us everywhere that links to this, everyone that like points at this expected result thing. So we can see that there's 2 locations that are looking at this expected result thing. The first one is right here. So where it's printing out the expected result, character by character, right? We've got K0 to 4, blah, 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 blah. The other place is right here, which is the mem compare, right? So there's 2 places, and if we use X, right, we can see everywhere that goes here. The other thing we can do is if we double click on win, right? Now we can just see the decompilation of win. So we can see that when we win, it says you win, here is the flag. It opens the flag, and then at some point it reads the flag, and then it outputs the flag. And if something went wrong, it tells us there was an error, right? So this is just what the win function does. And in the same way, we can select win and we can hit X on that. And if we do that, we can see everyone that interacts with the win symbol. And this right here, right, it calls win. But if there were multiple spots that called win, we could just select win and hit X, and that'll show us everyone that calls win. There's a whole bunch of different tools that you're going to develop while you're working on these challenges that aid you in reverse engineering and the process of thinking about how to reverse engineer, all the different little tricks that are involved in terms of thinking about control flow, thinking about function calls, thinking about X references, cross references. And this is kind of the goal of this module, especially the reverse engineering part. Now, one more thing I'm going to show is the .1 version, just to make sure everything makes sense here. So if I refresh to connect, and then let's just say I run the challenge, baby rev level 1.1, we can see it's ready to receive our license key. We say hello, and it just tells us checking the received license key, wrong, no flag for you, right? It's not giving us all that helpful information about how it's mangling it and what it's comparing against. This is just all it says. Can I do IDA 64? Nope, we should make that happen. Now, if we open this up, of course, in IDA, again, right, we're looking at a new program in IDA. We look at baby rev level 1.1, permission denied. That's okay. We're just going to save to our home directory instead. We're going to hit OK. And here we go. This is this program right here. And something's a little bit different here. The issue is that we are in a stripped binary. And what that means is a lot of the symbols just vanish. In all of these .1 versions, you're also missing a lot of symbols. And so what IDA opened us up to, because it could not find main, there was nothing called main, it just started us out at the entry point, that underscore start thing. It's kind of the difference, as you see in embryo GDB, between start and start I. But this thing ultimately eventually just calls main, and IDA has fancy ways of detecting and figuring out what main is. So it turns out that in the IDA world, there actually is a main, because it just intelligently analyzed the program and just kind of guessed what main is, and it probably guessed very accurately what main is. But that's why it started us here, is that technically there's no main symbol. IDA has just inferred where main is, because IDA is awesome. And then if we go here, right, so now we're in what IDA thinks is main. Another way that we could do that, by the way, so I just looked through this graph on the left. Another way we could do that is if I hit G, and if I type in main and I hit enter, it goes there. If I hit G and I type in start, it goes there. If I type G and I type in win, it goes, well, IDA doesn't know what the win function is, so there's nothing called win, but that is okay. So let's go back to main. And we'll hit OK. And now let's just do our favorite thing of hitting tab and looking at the decompilation, right? Looks very similar. It does receive our license key, checking the received license key, and it does this mem compare. Now you're going to notice here that it's not called expected underscore result. That's because the symbol for that is gone. But the data is still there, and IDA has randomly decided to call it this crazy thing. If we double click on this, though, we can see that it is NWMBT, right? Again, very easy. It's a level 1 version of the challenge. There's no mangling going on. And so we can see that we're totally fine. And then we can see, right, there's nothing called win, but there is this thing that if we compare it to the previous program, right, this is probably win. And something we could actually do is if we double click on it, like we can confirm, right, you win, blah, blah, blah. If I click on this and I hit N allows me to rename things. So also another thing you're probably going to end up doing a lot, probably not so crucial in this module, but in the general sense of reverse engineering, is going through and labeling tons of stuff. You can start adding comments. You can start doing all sorts of stuff. So what we're going to do is we're going to rename this to win. And now if I hit G main, And if I type G win, right now G win works. And if I hit X on this, right, we can see everyone that calls win. Now we can see it's called it win, right? We've just kind of updated the name of this function here. So again, right, we would look at this, we see it's this, we take this, go here. Oops, that's not going to work. New terminal, challenge, baby rev, this, pass it that string. Well, it's not letting me paste, I guess. I don't know what's going on there. NWMBT. What? Why is this being weird? This is feeling weird, but I'm going to ignore that for right this second. NWMBT. What? Okay, NWMBT. Enter, and it gives us the flag. Now, one final thing we're going to do is we're just going to look at a later level, just so that we're very clear of what's going on here. The first level of the challenges is easier, as we would expect. These later levels do crazier things. So if we look at 8.0 real quick, and then we're going to run the challenge. So let's do this. We open up this, we run this. Level 8, and I give it test, and I hit enter. We can see stuff starts happening, and this increasingly gets more difficult, but the input starts getting mangled. So we sent it test, right? We can see this is right here is test, and then new line, and it just starts doing stuff. Like it sorts our data, and then it XORs our data, and then it reverses our data. And then it swaps data, and then it reverses, and then it swaps, and then it XORs. It just does a whole bunch of stuff. And if we look at that in IDA, okay, new, level 8, okay, tab. All right, if we look at that here, we're going to see that the source code looks a little more tricky, right? We've got this right here that does this crazy nested for loop, and then this crazy for loop with XORs and stuff, and then, I don't know, just a whole bunch of stuff, right? The data is being modified and then compared. That's what's happening in here. And at some point, some of this, I don't know, it depends. Like in some sense, it might be easier to read the decompilation, but at some point, you might want to take some operation and look back at the disassembly and see what it's really doing. Because sometimes, normally the decompilation isn't like actually wrong. It's just more confusing than what is actually happening. So it's nice to use the decompilation to look at the program at a high level, see what's happening. And then if you need to drill in on some sort of thing and look at the assembly, believe me, at some point you're going to want to look at the assembly. The assembly might actually be, and I know it sounds insane, the assembly might actually be easier to read in some cases compared to the decompilation. And I know most of you here are not going to trust me on that. Eventually we'll learn to trust that. But the decompilation sometimes is actually more confusing than the disassembly for some small segment of code. Obviously, the high level decompilation is great. It shows us the general flow of the program. But at a microscopic level, there might be certain operations. Like, look at this. This is like crazy. And now you might be thinking, all right, it's also going to be crazy to look at the assembly. But the assembly might actually be easier to read than this, right? We're just doing a whole bunch of moves and subtract. You'll see. It all makes sense. It'll be great. Okay, are there any questions about IDA that anyone has? I know we're near the end of the class. Obviously, we'll have time in the next live session to answer questions about anything in general. I just wanted to make sure everyone has a good start on these challenges. IDA is going to be a very useful tool. And I guess one more thing. Is there a way to copy the flag from the desktop? That is a good question. So if I double click on, let's say, expected results, and I click this, and then I click this, we can see now I can copy this. This right here is how we can copy. So this just follows whatever I have selected. So we can use that. Yeah, there's a question. Definitely if you're going to want to jump into something like IDA. So the first 8 levels, you're just using GDB and you can probably use whatever you want. But after the GDB levels, probably there's different ways to approach the problem, but IDA is definitely probably going to be a pretty popular one and a useful one. And in that case, yeah, use the desktop view. How did you originally open the disassembly view again? I'm curious if you really mean the decompilation view, but let's show every way that we can do this. If we hit go, what? Apparently that doesn't work. IDA, okay, new, baby rev, there. Decompilation, all you do for decompilation is you just hit tab on your keyboard, tab. Or I think you can hit F5 also, let's see. Instead I do F5. I don't even know if this will work. Yeah, F5 also works. So F5 or tab will get you to decompilation. Where is the flag stored in the program? So that's a good question. The flag is not stored in the program. It's not stored anywhere in the program. There's nothing that stores the flag in the program. There's going to be some sort of secret slash, as we've seen, this expected result thing that after it does a bunch of mangling, blah, 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 blah. That's stored in the program. But eventually, it just calls win. And win opens slash flag. So slash flag, it's still just like all of the previous, it's the previous challenges. Technically, slash flag has been there, but you haven't as directly interacted with slash flag. Ultimately, though, it's just pulling it from slash flag. It's just reading it. And the program has the ability to read slash flag, even though you do not. How are you searching functions? It's going to be all the fun questions. I'm just typing G. So if you type G, it says jump to address. You can also put in a symbol. So win, main, start, underscore start, etc. So this is the decompilation for those curious about start. It just calls libc start main and passes main as the first argument to libc start main. Libc start main goes through, does a bunch of libc main stuff, and then libc main stuff calls main. I don't know what that means. It's possible to manipulate the memory in GDB to just call the win function directly. The short answer is yes, and you'll see that in level 8 of the GDB modules. And yeah, GDB is very powerful. So as I said before, or I guess I didn't necessarily say it before, in this case, we just looked at analyzing this program in IDA. This is kind of what's called static reverse engineering. The reason we teach GDB at the beginning through those first 8 levels is that we might also want to look at the program in GDB. In fact, in order to do that real quick with our last few minutes remaining, let's look at 1.0. Or actually, let's just start here. So what I'm going to do, sage hacker at dojo.pwn.college. Okay, so we've got our first level again. And if we look at challenge baby rev level 1, as we said before, all of this happens, right? And what we've learned is that eventually a mem compare happens. Now, it turns out that GDB is also very useful. And within the first 8 levels, you'll learn a bunch of things that you can do with GDB. And I'm going to show one of them to you right now on why GDB is so awesome. So if I type start I to break at start, right? We just start up the program, the very first instruction. I can look at all of the upcoming instructions that are about to be executed. In fact, I'm going to set disassembly flavor to Intel. This is how we can see it in the syntax we're used to. Set disassembly flavor Intel. We can see that eventually we call DL start. But what I can do is I can break on main and I can continue. And now I'm in main and I can do x/8i RIP. And don't worry, if I'm typing all these commands really fast, you're going to see in the first 8 levels, it talks about all of these commands. This is why GDB is useful. So as soon as you start learning all these commands and these ways of kind of using GDB, you can start quickly navigating and executing program. What that means is we're going to be doing also dynamic reverse engineering. So there's static reverse engineering, which means just like looking at the blob of the program and like making sense of it. And there's dynamic reverse engineering, which means going to some particular state in a program, right? We're paused at the very beginning of main, or maybe I cut 2 instructions and now we're right here in the program, or 2 instructions into main. We can go to all sorts of stuff. Now, what else I can do is I can break on, let's say, well, let's make sure we get this right. So we can see 100 instructions here, and we said eventually we've got, wait, did we not see it? 200i, RIP. Right, eventually we can call win, and eventually we can call memcompare. So if I just want to, so initially we did break at main, I can also just do break at memcompare. And if I continue now it's asking for input, and I said hello. Wait, did we not break at memcompare? What happened there? My demo, it's very sad. Oh, I broke it the wrong memcompare. Okay, hold on, let's start again. Break memcompare at PLT. And continue. So we could see before, it won't let me, X200i RIP, right? We can see right here, it calls it memcompare at PLT. That's why I had to do break at memcompare at PLT. So we did that. And then if we continue and we say test, we can see now we're in memcompare at PLT. And if I look at, let's say, RDI and RSI, we can see the exact arguments going in. Or I can dereference these things. If I print it as a string, RDI, that's my test that I passed it, or RSI, we can see that that's PXFFG. We can start doing dynamic reverse engineering. And you'll get a feel for it as you work on this module, what kinds of styles of reverse engineering feel most natural to you, what feels good for you to do. But there's kind of 2 paradigms, right? There's static reverse engineering, which means looking at things in IDA, just looking at the whole program, looking at all the possible flows and just kind of making sense of it, just staring at the whole program, versus dynamic, which means kind of going to whatever part of the program in its actual execution, right? We sent it test new line, and then we broke it to memcompare, and we can see the arguments going into this memcompare. So we can see here, it's PXFFG, here it's test new line. So we can tell that this memcompare is about to fail, or not necessarily fail, but it's going to say that they're not equal. Whereas if instead, and so then we continue, you can see here that didn't work. Continue, no flag for you. Whereas if I start again and I continue and I pass it PXFFG and I look at RDI, and RSI, right? They're the same thing. We continue, and suddenly the flag comes out. Well, this is where practice mode would come in. You'll see that it says you win. It failed to open the flag. The reason it failed is because we're using GDB, but this is the idea here. So we would just rerun what we did outside of GDB, and it would give us the flag. Okay, thank you all for attending. We're 2 minutes over, so we'll end it here. I'll be happy to answer questions about GDB, IDA, whatever things sound interesting in the next live session. Good luck, everyone, with the module.